Okay, let's get started. Assignment 1 is today. Anybody here have something they want to hand in? Okay, so you can also email it to me by the end of the day, as a PDF. Or you can give it to me right now. Sorry about that. All right, so
just a quick question: is the end of the day policy thing normal, or is that just this time? Because I saw on the site that it was by the beginning of class.
Yes, so I'm going to change that policy because if you want to hand it in a hard copy, then you should give it to me before class because I might not be here in the afternoon. So, but if you email it to me, anything by the end of the day is okay.
Okay.
Yeah. Just because of a time zone issue with all the remote participants, I'll just specify the day and leave it at that. Okay. Yeah, so originally usually I make it do at the beginning of lecture so I can talk about some of the things about the homework. But I'm going to start talking about it on Monday because that'll obviously give me a chance to look at your hand-ins and see what you guys did so I can discuss it on Monday. Okay. All right. So were there questions from last lecture before I move on? Any questions from last lecture? Okay, so some of the things we'll go over again. And so, so today I want to take this interpretation that we have of linear logic in terms of concurrency and extend this to more of the constructs of linear logic to see what they mean. Or another way to say it is we already know what they mean intuitively and in terms of the proof rules. Now it's worthwhile to see what they mean in terms of communicating interaction. Okay. So, but I wanted to draw a little bit of picture to see what we're doing here. So we started with something like this. So we have, delta proves A. And then we have, I'm going to write cut here, a cut reduction. Okay. And the reductions of cut preserve the thing that you're proving, right? So when we were checking whether you can do a reduction, that is, if you can match up the left rule with the right rule and reduce the cut to smaller types, the conclusion at the bottom always stayed the same, right? That's obviously part of definition. You change one proof into another proof, okay? And so then what we did is we kind of made a transition here. So we annotate these things. So the delta now has channel names. And then we have a process that offers a service, which we view A now along some channel X. And of course, the same thing happens over here. Okay. And then we just basically see, if you do a reduction of cut over here, how does the process term P change when you go from here to here? So it goes from P to P prime. Okay. So there is a cut reduction here, which relates a proof to another proof. And if you just look at the process assignment, you see that P gets turned into P prime. And in a different way, we were looking at process P here, and we're doing a reduction in the pi calculus to some kind of P double prime. Okay. And then we observe that these two things over here, even though they're not equal, they're what's called structurally congruent. Okay, so they behave the same way. They're not syntactically equal, but they're in some very strong way equivalent. Okay, and this strong notion of equivalence that we needed here was kind of some structural congruence. Anybody remember a law of structural congruence that we needed last time? Okay, so structural congruence. So we had P parallel with Q. Q parallel with P, P parallel Q parallel R is equivalent to P parallel QR. Okay, I might not have written all of these out, but there was another one that was a little bit more trickier. Yeah, Anton? Scope extrusion, exactly. If you have P in parallel with a name restriction on Q, then you could pull that out. Okay, and there was some condition on being able to pull that out. What was that condition? Right, X cannot occur in P. So X not in the free names of P. Okay. All right, so we'll see if we need anything else. Okay. Okay, so what we want to establish is that there's a very strong connection between, okay, and now we can put both sides there. So here we have linear logic, and here we have the pi calculus. Okay, so the linear logic propositions correspond to what's in pi calculus, what's called the session types. Okay, so linear proposition correspond to session types. Then the proofs here correspond to process expressions. And proof reduction corresponds to interaction or computation reduction over here. Okay, and if we're super successful, okay, these are all kind of isomorphic. Okay. Now we already know from functional programming that we can't always get that. Sometimes you don't actually get full sort of analogy of everything, but you might have an analogy up to a certain point. So we'll have to keep an eye on how well this correspondence works. Okay. Ideally, we like the two to be the same thing. Okay. So this is an example of what's called a Curry-Howard isomorphism. Okay. And that's because this kind of thing was first noted by Curry in 1934. And what he noticed is that if you do proofs in if you do axiomatic proofs in the style of Hilbert, okay, that the proofs can be given a computational interpretation as combinators. Okay, and so that's I think the term used these days for that is combinatory logic. Okay, and that you can reduce proofs and this corresponds to combinatory reduction. Okay, and then we had Howard in 1969 noticed that there's a very similar correspondence. And the correspondence here is between natural deduction and lambda calculus terms. Okay, and so there, the proposition of intuitionistic logic correspond to types of a simply typed lambda calculus. Proofs in a natural deduction corresponds to simply typed lambda terms, and reduction of proofs, the way it was described previously, for example, by Pravitz, corresponds to lambda calculus computation or reduction. Okay, he established a bijection of all these arrows, that these really exactly correspond to each other. Okay, and that's why it's called a Curry-Howard isomorphism. Okay, and it's interesting because basically this is combinators and combinatory reduction. This is natural deduction and lambda calculus. And now we're looking at linear logic and sequent calculus. Okay, so basically all the parameters change because the logic is different, but also the proof calculus is different, and we get a different notion of computation. So at some point later in the class, we'll look at this some more, because we're going to look at not the combinatory version, but we will look at this version as well. We look at natural deduction calculus for linear logic and how this is related to our sequent calculus. Okay, but first we have to complete this picture, because I've only shown you so far one propositional construct, namely A implies B. So what was the computational interpretation of that? Anybody remember that from last lecture? If you offer that service, do you remember what that was?
We expect a channel
Yeah.
which we pass A,
Okay.
and then we pass B back, both sides.
Okay. So if we offer this service, we input a channel of type A along X, and then we offer the service B along X. Carl?
Yeah, that's fine.
Okay. So as a service, it's an input. If I want to use that, okay, if I want to use that service, I have to output, right? Because if that's in my environment, it expects A as an input. Right? Okay, so now we're going to look at tensor. Okay, so the way this is going to play out is that A tensor B means you output a new channel Y of type A, and then you behave like B. Yep.
So why couldn't we, for example, expect the service A rather than a channel across which that's the service A?
Well, all the things that are communicated here are not processes. They're just channels, which are ways to actually interact. So the service A is identified with the channel. Yeah. So the only thing we can input here in the pi calculus is channels. Okay. Okay, other questions? You have a question?
I'm just waiting for the
Tensor.
opportunity to ask the question. I think that's the actual.
Okay, yeah. So I'll postpone that because let's go through some more and then we can reconsider that. Okay. So X A tensor B is going to be output a new channel Y of type A and behave like B. Let's see how that works. Okay. Okay. So let's look at the right rule first. Okay. So we have to remind ourselves what the right rule is for tensor. So we have two contexts, delta and delta prime, and we have A tensor B, and we have to devote some of our resources to get A, and another portion of our resources to get B. Okay, and now we're going to put channel names on that. Okay, so we're offering X, we're offering that. Okay, so the way this is going to work is that we're going to create a new Y here, and instead of creating a new channel over here, we're going to reuse X. Okay. So we could have equally well put X over here and create a new channel Y over here. Okay, and then the meaning would have been output a new channel Y of type B and then behave like A. But it makes more sense when you read the type as a kind of a contract for an interaction to read everything from left to right. Okay, so intuitively it makes more sense for this Y colon A to be something that you output and then you behave like B. Okay. Okay, so what happens now when you put the process expressions here, we get a P over here, we get a Q over here, and then we output a new Y. Okay, we create a new Y, then we output that along X. Okay, and then we have P in parallel with Q. Okay. Sorry, I ran out of space here. Okay. So we actually don't need any new process expression because we already had output. Actually, let's put the process expression over here just to track them. For initial sequence, we had channel forwarding. Then we had name restriction. We had parallel composition, P in parallel with Q. We had input of a Y along X. And we had output of a Y along X. Okay. I think that's all we needed so far. And we don't need anything new here because we're just outputting a new Y. Okay. And then we have P and Q executing parallel. Okay, so now we have to see what's the matching left rule. So we have delta, and we have a tensor B, and we're trying to prove C. Okay. Anybody remember what? Everybody hopefully remembers what the left rule is for tensor.
You have delta A, B on the left.
You have delta A, B on the left, and you're trying to prove C. Okay. So we have, it means simultaneous conjunction. We have both of them in the same state, so we break it up into two pieces. Okay. So now we have to label these. Let's put Z over here and X over here. Okay, so now we have to decide how to label these two premises. Based on what I did over there, how would you label them? Yeah, Anton?
Y for A and X for B.
Yeah, so a new y for A, but I'm going to reuse the x for B. Okay. And now what's the process expression? Well, there's going to be some p here, or let me call it r. Okay. And so now, what is the computation interpretation of this? Yeah?
I think you want to input along X, and I'll give you what is actually the Y above.
Okay,
And
so
what you name, I don't know.
okay, so we input along x or y. The y will have type A, okay, and then we continue with x colon b. Okay, so let's see if these two actually make sense together. Okay, so that's the tensor right, and this is the tensor left. So we can do a formal check, but it takes a long time to do that, so I don't want to go through all the details. But essentially, we're doing the same thing, okay, as before. We can reduce this cut on the pure calculus. We can see what happens to the proof terms, and we can do the pi calculus reductions and see that they're the same. Okay, but it turns out we don't need any new reductions in the pi calculus because it always matches. It still matches an input to an output, but just now different in the polarity. Okay, so according to our interpretation, okay, A tensor B outputs an A and then behaves like B. Okay, that's what I said. It output an A along X, a new A, and then behaves like B. Okay, and so if that's in our environment, okay, we have to expect that Y as an input because the environment, this X is going to output something while we're ready for it. Okay, we input that and then continue with R. Okay, and when we continue with R, we now know that the channel X behaves like B, so that'll be correctly typed. So that conversely, if we're supposed to offer this service, okay, we have to output the Y of type A. And while we have that here, it's a new Y, and we have a P which should actually realize it. So P now will communicate with this R, which contains Y. Okay, so this P here can communicate with this R if we have a cut between the two. And then we'll continue on the chain angle X, okay, offering B, which matches what R expects to be in the environment. Okay. Okay, so these two actually match up, and you can do the writing down. And maybe I'll give you a chance to make sure that you understand that by having you write it out, okay, in the homework assignment. So are there questions on this? Yeah?
So I think the stimulus function happens here. Is it possible to grab P out of the derivative so that it doesn't have to wait for the X?
Okay. Okay, so let me rewrite this. So here we have P in parallel with Q. And that's going to be, what was it here? X colon A tensor B. Okay. So let's see what depends on what. So the P depends only on Y, okay, and the Q depends on X, right? Okay, because you can always see from a judgment what a process can depend on because it depends on the channel along which it offers a service, and on the left-hand side, the channels that appear in delta and delta prime. Okay, so P depends on Y and Q depends on X. Okay, so the question is, do we have to wait here, okay, at this point, or could we put the P of Y on the outside, okay, so that it can interact with its environment before this has taken place, okay? So could we ascribe this one, I guess is the question, nu of Y, and then we put P sub Y in parallel with X, Y, before Q of X. Okay. Okay. I'm inviting opinions, whether that makes sense, and what the consequences would be.
And mu there only restricts
Okay, so the observation is that this nu of y question is who produces the channel and when. If that doesn't actually produce the channel is really produced here, then it might not make sense to do that. But I guess this thing only outputs the channel. We really have to think, I guess, of nu of y as somehow creating the channel, right? So maybe that would be okay. Any other comments on this rule compared to this one? Okay, say that again.
Well, we want the By and Qx to interact, right?
Okay, so they interact but not with each other, right?
Yeah.
Because they don't share any variable in common in this particular case. So it looks to me as if the first thing to notice is that because y is created here until this is being sent, P cannot really communicate along y because there's nobody else listening. Make sense? Okay, because this action will output the y to the environment. Somebody is listening at x, right? The client is listening at x when we cut this with something that uses x. There's a client listening in x for a name and wants to communicate, okay, get a name and then communicate with the service that provides that. So somewhere there's a client waiting for y, okay? Now, if we do this like that, then P of y is going to sit in the context, but nobody can communicate it until this output happens. Correct? Because there's nobody else waiting for it. Do you see that? Okay, because the name is restricted here until it's communicated along x. It's nowhere else. So no other process can work with y. Okay? So we certainly, P cannot communicate along y until this thing actually happens. However, we do have a little bit more parallelism here. Because if P is itself a computation, like a cut at the top level, okay, that kind of communication could take place before this is sent. Okay, you see that? Okay, so if P itself would be a cut, right, there's some communication that has to happen before it's ready to communicate along y. In this form, that communication can happen. In this form, it couldn't happen, right? Because here, it wouldn't be exposed until this prefix here is being removed. Okay. Okay, and so this comes up to a particular difference between interaction in the pi calculus and proof reduction, okay, which is that proof reduction in some sense is agnostic as to where it happens. Proof reduction just says we have a proof that looks like this with a cut, with the left rule and the right rule, and we can reduce it to another cut. Okay. It doesn't say that it has to be at a particular place in the proof, at the outside, the inside, or anything like that. It just says we can reduce it. Now, pi calculus reduction, the interaction actually has some discipline to it. And so, for example, even if something can be reduced inside P or inside Q, these reductions will not be enabled until this output has actually taken place. Okay. So the pi calculus forces some kind of outermost, okay, strategy of reduction. Okay. And so indeed, so if you made this kind of proof term assignment, we would have more parallelism in the sense that some reductions in P of y could take place that are actually prohibited over here. Okay. So another remark I want to make is that the way we're actually conceiving of the pi calculus here, it's called synchronous, okay, in the sense that the interaction rule, okay, which is if you have an input along x of a y, and then P, and I put that in parallel with an output of a W, and then Q, that moves to, what does it move to? P in parallel with Q. And how do we modify P? We have to substitute the name W that I sent for the Y, W for Y. Okay? So this is synchronous in the sense that the interaction has to happen, this has to input, and this has to happen in the output in one step, and then P and Q both can continue. Okay. Now the asynchronous pi calculus does the following thing. When we see an output here, we can send it and continue with Q before it's being received. So we don't care if it's been received, we just continue computation. That's called asynchronous computation because the two endpoints don't have to agree to the communication at exactly the same time. Okay. So doing an assignment like this goes more towards the asynchronous version of the pi calculus because it will allow some other things to take place as if this output has already happened. Okay. But it's not just this one change doesn't really give you the asynchronous pi calculus. So at some later point of the semester, I might talk about how to get, by a Curry-Howard interpretation, also the asynchronous calculus. Right? And I can't talk about it right now because we haven't it completely figured out yet. Okay, so we're still working on that. But this is a step in that direction. Okay. Are we okay on this? Or are there more questions on it? Okay. So let's continue with choice. Actually, do one more thing, unit. So x:1 means terminate communication on the channel x. Okay. There's no continuation. Okay, so this is the unit of tensor. This outputs something and then continues like b. Here we don't have anything to output because and we have nothing to continue with because there's no second component. So we just terminate communication on the channel. Okay. Okay, so I'll erase this and show you the rules. Okay, so the right rule. So the right rule requires the context to be empty. And there's no premise. Okay. And so the notation for that is something like this. Okay. So basically, we don't output anything, but it behaves like an output because it's the unit of tensor. Okay. And then we terminate, and termination of the pi calculus written as 0. So we have 0 down here. And we also have a version of input and output which take no arguments. So I should probably write an overline here to emphasize this is an output. Okay. Okay. And then the left rule is usually like this. So we have delta, we have 1, and we're trying to prove C. And we just throw away our resource. Okay, and so this is going to be a channel X. Any guesses what this might correspond to? Yep. So we input nothing, and then we continue like P. Okay. And then the reduction rule corresponding to this is somewhat like this. So we have an empty input P in parallel with an empty output of Q. Whoops. And then we go to P or Q. P and Q in parallel. Okay? This is usually not done in the pi calculus, but this is something that you would call, I would call a synchronous termination. Okay? So when you terminate a channel, the endpoints have to agree on the termination. Okay? So it doesn't have a lot of parallelism, and you lose some parallelism doing it that way. And so in the original paper on this, we actually gave up on the full isomorphism between proofs and process expressions in order to recover some more concurrency, some more parallelism. And the way we did that is that the left rule is silent. Okay? So if something in your environment wants to terminate, let it. I don't care. Let's not wait for it. Okay? So this is like waiting for X to terminate, right? And so we don't have to wait for that. It's just going to go away on its own. So we don't have anything here. And then this prefix goes away, and 1 just corresponds to 0. So that's an alternate way to assign process expressions. Okay. So this one goes away here, and this part goes away here. And so then termination is essentially asynchronous. The endpoints of the channel don't have to agree. The channel just disappears. Okay. Does that make sense? And you recover a lot of parallelism because it lets P continue without waiting for X to terminate. Okay. But the price that you pay is that you no longer get a bijection here, okay, between the proofs and the process expressions. Okay. So in some sense, there's more proofs than their process expressions, because no matter where this one left rule is applied, one right, one left, no matter where you apply it in the proof, okay, the process expression always stays the same because we don't have a prefix. Okay. Okay, so this is a subtle point, but for certain properties of the calculus, it can be significant. Okay. So the next thing I want to talk about is choice. Okay. So let's do that over here. Okay, so our intuitive understanding of A with B so to try to prove that, what do we have to do? A with B. Anybody remember what that means? Yeah?
Prove that you can get either A or B with your resources.
Okay, so you have to be able to get A with your current resource and also B. Yeah. Okay? If you use that, consequently, if you know that you can use A with B, what do you have to do? Yeah?
Pick one and you continue with it.
Yeah, you have to pick either A or you have to pick B, right? So in the menu example, it was if you pay $50, then you get a choice between a soup and a salad. That's your contract with the restaurant. You have to make that choice. You have to pick one or the other, okay? And the restaurant has to be prepared to prepare both of them. Okay, so now the question is, if I do this, what would we expect? If we offer the service A with B, what would the client be able to do with that?
Some sort of selector and the server sends back and forth them.
Exactly. So at the client, I have to send some selector over to the server, okay, and tell it whether I want the left or the right. And then the server would respond with either the left or the right, depending on what I do. And that's exactly how it works. So we have the right rule is, actually, let's do the left rule first, because in this case, okay, and I'm trying to do, okay. So I'm going to reuse the same channel for A, right? And I'm still obligated to provide that, and I get some process P. Okay, and so all I need to do now is, before I continue with P, I need to send a selector. And we'll take this notation. Along X, send in left, INL. Okay, continue with P. Okay. So we need in the chi calculus a selector now here. So we need to say, along a channel, select the left alternative and continue with P. And we can also select the right alternative and continue with P. So this is in left, in right. Okay. And in right, of course, here will be X colon B, right? I don't have to write that down, I don't think. Okay, so now on the other hand, if I'm obligated to provide A with B in some context delta, then I have to show how I can get an A, and I have to show how to get a B. And this is going to be along some channel X. And this is going to be the same X, and let's call this P. And this is going to be X, and let's call this Q. Okay, so now what process expression is going to be here to realize A with B? Ian?
We're going to have some kind of case.
You're going to have some kind of case, right? Because we have to account, we might be sent in left or we might be sent in right. We have to account for both cases. So we say case, x dot case, and then we have the two branches, P or Q. Okay. So this is weird, a little weird, right? Because when you know functional programming, you would expect that A with B is like a product. So it's a pair of two things. But here it turns out to be a case construct. Okay. But it still pairs up P and Q, right, as the two branches of the case. And which one you take is based on X. Okay, so it's a little strange, but hopefully not overwhelmingly so.
It's a case in the intro rule instead of the limit rule.
Yeah, right. Yep. Okay. What would be the reduction? Let's check one reduction. Okay, so if you cut this is the first left roll and this is the right roll. If you cut this one with this one, what does the process expression looks like after the cut? So maybe I should rename, in order to make this sensible, let's call this Q and let's call this R. So this is Q, case QR. Okay, so we cut this with this. Okay, so I don't want to write the whole cut. I just want to write the process expression. So somebody should be able to dictate it to me. What's on the outside? First thing on the outside. If I cut this thing with this thing. New X, right? Because I am communicating along a private channel X. Remember, cut the outside is a new X. And then I have the two pieces that are underneath in parallel, right? Okay, so what do I get on the left? What is the first component here?
X dot now.
Actually, because this is the right rule, and the right rule occurs in the left premise of a cut. Sorry about that. This is actually the case part. Case QR. Okay. In parallel with, and here we have X dot in left followed by P, right? So that's just the cut, right? So remember, a cut is always a name restriction because we communicate along a private channel, and then we have the thing that realizes the service here, and then we have the consumer over there. Okay, the consumer says, give me the soup or the salad, and then that has to react. So what do I reduce this to? So this is a reduction. So in this case, we send in left, right? So what does it select from these two?
Q.
That selects Q. And what happens over here? It's just P, right? We continue with P, okay? Now, is that actually the same reduction as happens in the sequent calculus? Okay, let's put it here. Because we want to check that the reduction corresponds to the way proofs are reduced in sequent calculus. So let's think about that. So in the sequent calculus, we have delta proves A with B because delta proves A, delta proves B, and delta prime. A with B proves C because delta prime proves A. Then we do our cut. Delta prime together with A proves C. We do our cut, and because delta prime proves C. And what does this get reduced to in the sequent calculus? Okay, remember the reduction here? So this is the width right. This is the first left row. Yeah?
You're going to cut delta proves A into delta prime A proves C.
I cut these two. So I have delta proves A with delta prime and A proves C. And then I get delta together with delta prime proves C. Okay, does that correspond to this?
Yeah.
Okay, let's go over there. What was Q annotating? Q was providing X along A, right? So Q is the proof of A. What was P annotating? It's up there. P annotates proof of C from A. And what we're cutting out here is exactly X, which has A. So it's really the cut between this and this. So that corresponds exactly to this cut. Okay, so we do take a cut at A with B, and we're reducing to a cut at A. And that's the corresponding pi calculus reduction. Okay, so it works out very nicely. Okay, it matches exactly. Okay, so now we need the meaning of all of these. Let's see. Anybody care to guess what that is? Or actually, no, don't guess. Tell me what it means intuitively. If you have to prove A plus B, yeah?
It means you're going to be given something.
Hmm?
It means when you have it, like you, like instead of sending a selector, you'll have a selector.
Okay.
That's a case analyzer to make use of it.
Okay, I think that's the second step before the first one. What does it mean in linear logic before we get to the processes?
You send something, but the client cannot choose what.
Right. You're thinking about processes now every time you think about the linear logic. We're not sending anything. How do I prove A with A plus B in secant calculus?
You have more than two choices.
There are two rules, but I have two choices. I can prove A or I can prove B. Right. So therefore, if it's in my context, if I want to use it, how do I use A plus B?
You have to case on it.
I have to case on it. I have to analyze, right? Because it could be this or it could be that. So there's two premises. Okay. And so now your two answers are the right ones. Okay. So when I prove that, I have to indicate which one I actually proved. Did I prove A or did I prove B? So when I provide a service, it's my choice which one I provide. So I tell my client, oh, okay, I provided A, I provided the thing on the left. Or I tell the client I provided the thing on the right. And if I'm a client and I use that, I have to case, because I have to account for the possibility that the server sends me either an A or a B. Okay. So it's completely symmetric to the one that we did just now. Okay. Just the roles of the client and the server are being reversed. So I'm not going to write it out, but you can certainly read it in the paper, or you can write it out yourself, but it's completely symmetric to that. Okay. Okay, so let's look at what we have right now. We have, so this is from the point of view, let's take the point of view of the server. To provide this, I have to input an A, behave like B, output an A, behave like B, terminate, permit the client the choice between A and B, or another way to say that is I input a token that tells me whether I go to the left or the right, and then do one or the other. And here I output a token saying whether I want to go to whether I provide this or provide that, and then continue to provide that. Okay. From the point of view of the client, when I see X in the environment, I have to send it an A and then communicate with B. I have to input an A because that's what the server outputs, and then communicate with B. Here I have to wait for the termination. Here I have to send the server either in left or in right, and then continue to communicate with A or B. And here I have to input from the server the idea we're going to the left or we're going to the right, and then I have to communicate with A or with B. Are we okay on this interpretation? Okay. So the main limitation that we have right now, actually let's do an example. Okay. Okay, small example. I was afraid someone would ask that. Okay. X colon 0. Okay, so what does it mean intuitively? How do I provide that service? You can't provide it, right? Okay. How do I use it?
It sends you anything you want.
Yeah, okay. I think the best way to think about this, if you want to, is to combine these two, actually. Okay. and think about them as a sort of a logical representation. But what we really want is that long x, we offer a sum over some I of labeled services. Okay. So instead of writing a plus b, or writing a plus b plus c, or a plus b plus c plus d, I'm saying there's a whole bunch of services I'm offering, right? But I label them so that if you want, actually this is, okay. As a client, I know that the server will send me one of them. I don't know which one, right? But it'll tell me the label, okay? So what happens is that the labels take the place of in left or in right. I don't indicate by position which one I get, but what I send is the label, right? And saying, okay, it's the ith component, okay? So if there's 0 of these, right? Okay. If it's an empty sum, it means that the server will not be able to send me anything, okay? So I don't have to be prepared for anything. So basically, I can declare success, okay? If the client can send me 2 different things, I have to be prepared for 2 different possibilities. If the server can send me 4 things, I have to be sort of ready to accept 4 different things. Okay, so it's kind of a degenerate case, right? Yeah.
Does the same thing apply to the top, the T as well?
Yep. So that would be X has type some services all labeled. Okay, so that means the server is willing to offer me all these services, each of them with a label, which is like a tag or a name for that service. And I have to send to the service the label I instead of in left or in right. I send it the I and say I want the ith one. And so as the server, I have to be prepared to produce any of them, okay? Because I don't know what the client is going to choose. So if there's a choice between 0 of these alternatives, okay, then it's not a very useful service because the client can't ever get anything out of it, right? Because what can I send it? Well, I can't send it anything. So it just sits there in the context, okay? So x colon top is an unusable service, okay? We can never use it because there's nothing we can do. There's no component, okay? Okay, and that corresponds to the fact that there's no left rule for top in linear logic, only the right rule. Okay.
So the only way how to get rid of it, there is no way
Well,
except the X.
yes. So there is a way to get rid of it because you can prove, for example, this.
Oh,
Yeah. So, or you can prove this: top 0 proves 1. Okay, because that's the left rule for 0. No matter what's in the context, we can terminate. Okay. So I think in the context of these the session types, these 2 special cases aren't particularly interesting, except they're kind of degenerate cases of these 2. Okay. Okay. An interesting thought, and we haven't followed this up, but I think it's been done in other session type disciplines, is that a nice thing about this is that you can do subtyping. Okay. So you don't actually need to know all the services that are being offered as long as you have a handle on the one that you actually want. It doesn't matter what the other ones are. Okay. Which is difficult to do with this because of problems with coherence. But I don't think I want to go further into detail. But it's a good question. Whenever there's a binary operator, there should be a red flag going up. Okay, what's the unit doing? Okay, so here it turns out they're not particularly useful. Yeah?
So we didn't mention it in the logic either, but if we've got top, what's bottom?
Okay. So this is one answer because that is the unit of this. Okay, so that's 0.
Okay.
Okay.
I don't know, I figured if we had 1 and 0 separately, then we probably had some other dual symbol for...
Yes. So, so what is bottom? So the point is that 1 looks like this. So with no resources, I can prove 1. Okay, so if I dualize it, if I get bottom, okay, the right-hand side would have to be empty.
Okay.
Okay. That would be the bottom left rule. Okay. And then what would be the bottom right rule? Any guesses? Hmm?
Probably should be one.
No, 0 is the one that doesn't have a right rule. Bottom has a right rule. I'm giving away that much. Yeah?
I can add arbitrary number of bottom, something like this.
Not quite, no.
Could have some sort of contradiction on the left.
Yes, but what is the contradiction? Not sure. Ouch. No. I'll ignore that remark. I can post-edit the tape and take it out. Okay, no, it's actually pretty simple, right? So we have to allow right-hand sides that are empty in order for this rule to even make any sense. But how did we get it to be empty? Well, there was a bottom there in the first place. Okay. Let's see. We should always check that these things make sense, right? Identity expansion, cut reduction. Agreed? What would be identity expansion of bottom proves bottom?
Apply the right rule and then the left rule.
We apply the right rule to make the right-hand side empty, and then we apply the left rule. So bottom right, bottom left. Okay, identity expansion works. Okay, what would be cut? So we would have delta proves bottom, delta comma bottom proves C, then delta proves C. So now it becomes interesting, because now we'll know if this connective makes sense or not, right? Okay. How would we reduce that? Okay, well, this would have to be introduced by the bottom right rule. And this would have to be introduced by the bottom left rule. Actually, sorry, this should have been delta and delta prime. Now, how do I apply the bottom left rule? In order to apply that, C would have to be empty, right? Okay, and delta prime has to be empty. And I have no premise, right? Okay, so, delta prime is empty. Sorry, there's no here. So can I reduce this?
Just the upper left.
This one is the same as this, right? So yes, it makes sense as a connective. We found one more connective. All right. Hmm?
Do we have a binary case for this?
Oh. Okay. Do we have a binary case for this? You're really set on derailing the lecture today, right? Okay. So this is the inverse, right? Whenever we have a unit, it should be a unit of something, right? Okay. Somehow I've trained you too well. Okay, so what would be the left rule? Okay, so we have A, some new fancy operator. Okay, okay, I'll just call it par. B. Proof C. Okay. All right, what would be the left rule for that? Okay, what we have to do is we have to generalize the zero area version, right? So we have to generalize this to take two components. How would that work? Yeah?
Prove both you have to prove two stuff.
Okay, so here we have no premise, okay, for the left rule, so we have to have two premises. Make sense? That's from zero area to 2. So you were right, we have two premises, okay? So we have an A over here and we have a B over here. Are we correct so far? Okay, now the context there is empty. There are 0 components to the rest of the context. How many components to the rest of the context do we have here? 2, right? Okay. Part of which goes to the one premise, part of which goes to the other premise, right? So there would be a delta over here and a delta prime here. Okay. Okay. Now, how many conclusions do we have over there? Okay, so since this has 2 components, how many conclusions do we need? 2, okay. Okay, and how do they distribute between the 2 premises? Well, we need 2 conclusions for the rule to make sense. So one goes here and one goes here, right? Okay, so this is exactly the problem with this rule, or with this connective, right? If you want to have a zero reversion, we need an empty right-hand side. Okay, we haven't really discussed what that actually means, but that's what we need, right? If in order to make sense of par, we need to have 2 things on the right-hand side. Okay, and what does that actually mean to have 2 things on the right-hand side? So, unfortunately, because I'm an intuitionist, I can't really explain that. Okay. So we need to get a guest lecture from some kind of classical logician, okay, in order to explain why that really makes sense. Okay. What would be the right rule for this? Well, we might as well go a little bit further, right? So if you have C par D on the right. When I first learned about linear logic, I had to practice like half an hour before I could draw that symbol. Okay. So I now have to draw on all that experience. Okay. So what's the right rule for this? So let's look at the right rule for bottom. What does it do? This one here. How many components to bottom? None. So we get how many things here? 0. There are 2 components. How many things do we get on the right? 2. And what happens to the left-hand side there in the bottom right rule? Stay the same, right? Delta, delta. Okay. So now you should be extremely suspicious of that. Okay, not just because I'm an intuitionist, right? But what now happens when C itself is like a par? How would you break that down?
Then you get more.
Then you get more, right?
Looks like tensor on the other side.
Yeah, it's like tensor on the other side, but it's not good enough to just have 2 things, right? We have to now allow arbitrarily many things on the right-hand side. So what this rule looks like, I have some kind of sigma here, I have a sigma here, and this doesn't really look like that. What it looks like is I have some sigma and some sigma prime, and some sigma goes over here, and some sigma prime goes over here. Okay, so, and then there's a special case where sigma is empty. Okay, and then I get bottom. Okay, so to explain bottom, you only need to explain what the empty context means, the empty conclusion means, which we haven't done, but that's what we have to do. If you want to explain what par means, we have to have arbitrarily many things on the right-hand side. Okay, so it's a snowball, right? Yeah.
And so then do you change ID so it moves like everything in the context into the conclusions, or?
What do you mean it?
Like would A comma B comma C turnstile A comma B comma C be true by ID or not?
Oh, no, no. Identity rule doesn't change because there's no weakening. So if there were other things allowed, okay, that would really not make sense.
But like, since we have like multiple things in the context, like it would make sense to have like delta and tails delta.
No, not really, because on the left-hand side it means tensor, and on the right-hand side it means par. And so what you're really asking if A tensor B proves A par B. Okay, we can ask that. Okay. Does A tensor B prove A par B? Okay. What can we do here? Well, we can break this down, A comma B. And we can break this down. We get A comma B, right? And so now the problem, there's too much stuff in the way. Okay. Now, when Girard wrote his original paper on linear logic, he discussed a rule that he eventually rejected, but he discussed it, called the mix rule. And the mix rule says, if I have delta and I have delta prime, I can put them together like that. Okay, something like this. I should have written sigma there, not delta. Okay, so you can put them together like that arbitrarily. Okay, if you have the mixed rule, then you can sort out this mess, and you can put A over here, and B over here. Okay, and then it works. And then it's in fact the case that this proves that. Okay, but he rejected it, so it's not part really of true linear logic. So we don't have that rule, so we can't prove that. So this does not imply that. Yeah. Somehow that would have been too easy. Okay. Okay. Any further questions? Yeah, so I wish there was a really good explanation of this, but I just can't quite get it. Yeah?
I think I heard something along the lines of having multiple conclusions on the right can be interpreted as like the stuff you have on the left, if you have all of them true, suffice to prove that like at least one of the things on the right is false.
Correct. So that's true for intuitionistic logic if you're trying to give that some kind of interpretation with multiple conclusions. This doesn't work in the linear case, because if you're saying all the stuff on the left proves one of the things on the right, you would be incorrectly ignoring all the other stuff on the right. It still has to be linear. So that particular interpretation is...
One of the things on the right is false, but one of them is true. The conjunction of the left and the disjunction of the right.
Yeah.
Yeah, that makes
Yeah. So with all the conjunction of the things on the left, you can prove the disjunction on the right. Or another way to say it, if you have all these resources, you can achieve one of them. But that's not quite true. That would be plus. We have to make a choice which one you prove. But with par, you kind of have both of them, but you don't really prove both of them. So it's...
right.
Yeah.
Okay.
Okay. So it's a failure of mine that I can't really explain this, even though as a sequent calculus it makes perfect sense. Okay. So I have tried to understand it, but I have failed to do so. Okay. I've learned how to write it. Okay. That's how far I got. Okay. But I have written a paper with a student who was in my linear logic class when I last taught it in 2001, okay, where I gave an interpretation of the classical sequent calculus into the intuitionistic one, okay, as a final desperate attempt to understand what it means. Okay, so if I can't understand it directly, maybe I can understand it by translation. Okay, and that worked. Okay, so I can explain it to you by translation by telling you how I can read this. This is like an intuitionist attempt to understand classical logic. If I'm an intuitionist and a classical logician does a proof that I can't understand, I can translate it to my own language. Does anybody know how to do that? Anybody happen to have no?
Adding a lot of not.
Yes, it's called a double negation interpretation, which is related to something that Ian is working on. Yes?
Yes.
Continuation passing style. Okay. So there's a lot of connection to programming language. So it can be done, and it works for the connection between classical and intuitionistic logic. It also works for the connection between classical linear logic and intuitionistic linear logic. Okay. So I won't be able to do it in the last 10 minutes. Okay. But I will do it since this question comes up. Okay. So this is why this class is interactive, right? Because I don't have a set agenda, so we'll just see what comes out. Okay. But I do want to talk about exclamation mark because I want to complete this picture that we had over here. So these are the things that we had so far. So far, everything is strictly linear. Okay, there's no slack. Okay, no replication. But we already know that in linear logic there is a way to have things that are persistent. Okay, and okay, so And the connective is, of course, A. And we distinguish this by two judgments, right? Being persistent and being ephemeral. Okay. Does anybody remember the rules associated with that? With persistence, the rules associated with persistence. So first of all, you have to remember that we generalize the Sefton calculus like this. So these are the ephemeral ones, and these are the persistent assumptions, right? Okay. So, what were the rules for persistent assumption? Yeah, Anton?
Without using a persistent judgment, it's something like if you can prove A with an empty ephemeral context, then you can prove it persistently.
Okay, if you can prove A, then with an empty linear context, then A is true persistently, and it's okay to use persistent assumptions. Okay, so that was one thing. What was the other thing? Yeah?
If gamma with, of course, A, if it proves B, then gamma common A with an empty context. Semicolon.
Okay, semicolon delta. Okay.
See how that's, if gamma sits at semicolon delta, comma, of course, A proves C.
Okay. Okay, I put the line on the wrong side. Okay, so that's the of course left rule. What else do we have? We have a rule that doesn't really actually use bang, but just talks about the persistent assumptions. Copy rule. So if you have a persistent assumption, we can make an ephemeral copy of it. So we get the delta we had, and we add another A into it, and then we continue with C. Okay. Okay. So how do we justify this? Okay. We justify it because whenever we prove that something can be used persistently, it doesn't depend on any ephemeral resources. So if we need another copy, we can get another one. Okay. We can reuse this proof as many times as we need, okay, to get an A, because there's nothing that we have to consume to get an A. So A is somehow intrinsically true. It doesn't depend on anything that's ephemeral. So we can generate as many copies as we want, in particular here. Okay. All right. So we also disqualified this as a rule on a technicality, but this is in the intuition anyway. Okay. Now we also have a rule of cut, a new rule of cut, which is this. So if I can prove A from no resources, and I have a persistent resource to prove C, then from gamma and delta together I can prove C. Okay, so this means, okay, even though A is considered ephemeral on the right here, if I don't need any resource, that's the same thing as being persistent. So this is, I can construct a persistent A. This uses an A that's persistent. Okay, these two are in balance, so therefore I can get a C without using A at all. Okay, yeah?
Why didn't you write the rule that you just erased with an exclamation point instead of writing ephemeral and persistent?
Okay. Yeah, there's one more rule, okay, that says that if I want to prove, of course, A, then I have to have no resources and, oops, I can prove A. So that's the right rule. So there's a small intermediate step hidden here, which says that bang A to be ephemerally true means A is persistently true, which means that A is ephemerally true without using any assumption. Okay. So there's kind of a hidden intermediate step here. Okay. Okay, so for the discussion of today, we actually only need the copy rule and this rule, this cut rule. Okay. So the other rules we can ignore for the moment, because I just want to give you the computation interpretation. Oh, it must be very close to the end of the lecture. Okay, of that. Okay. So the question is, what does it mean? What does this rule mean here, computationally in the pi calculus? That's what we're looking at. Of course, many of you don't know the pi calculus. We'll have to figure it out some other way. Okay, so what I'm going to do is I'm going to do these assumptions like that. I'm going to introduce, these are, we call them shared channels. And they're not treated linearly. And it makes sense because the things in gamma, right, this is a semicolon. The things in gamma are propagated to all premises in all the rules. Okay, and they can be duplicated many times. So these shared channels are not linear. Okay. Now, what the copy rule does, it actually gives me a channel which now is linear, at which I can communicate as if it were x. Okay, and let's call this P. Okay, so now I only need to figure out what do I put here as a process expression in order to make sense of this. Okay. Any ideas?
Need a new x, and then you want forward u.
Almost. So I'm not quite forwarding, but what I'm going to do is I'm going to send x to you. Okay. So. And then I'm going to have p, and p depends on both x and u. It depends on u because I might communicate on it again. And it depends on x because x is the name of the copy of the channel. So what I'm going to do is I'm going to give this shared channel, okay, here's my channel, please communicate with me on that. Okay, so it's sort of like an HTTP service or something like that, where you spawn a new process when you get a request. And now you communicate with that new process. Okay, so there's a persistent offer for service A. The way I can get a particular instance of it is just by sending it a new name. And now I communicate along that new name. Okay, and that new name is actually linear. Now, because I've sort of made my ephemeral copy, is the new copy that I communicate with. Does that make sense? Let's look at the counterpart to make sure that it really does make sense, because that's the only way to check. Okay. Okay. So the counterpart would be. So this is the copy rule. The counterpart would be the cut rule. Okay. So we have to figure out how that works. Okay, let me erase this. So this new cut rule. All right, so we have gamma and delta. And we have gamma and nothing, colon x, colon a, gamma, comma u, colon a, together with delta, q, colon z, colon c. Okay? All right, so all we have to do now, okay, is to figure out which process to put here that corresponds to composing something that offers A persistently along a channel X with something to use a persistent service U. Okay. Okay, how do we do that? Yeah, have an idea?
So we're going to be receiving in a new name according to the copy rule.
Yeah.
And we have a name which was X.
Yeah.
So we'll be receiving a new name over U. And then we'll be forwarding that new, so Y.
Okay.
And then we'll be forwarding X and Y, the service providing A with the new channel requesting A.
Not sure what to write here to say forwarding.
The link, sorry, the X arrow.
Okay. So X, arrow Y. Okay. And what else? we need to run P. And of course, Q has to run. Let's say Q depends on U, P depends just on X. Okay, something like this. So let me, well, let me suggest a simplification. Instead of inputting a Y and equating with X, why don't we just think of X as being the thing here? So we input X and then P, because P already depends on X, right? Like Q depends on Z. So if you just call it X, that should be okay, right? So the binding here is just an input, okay? So we just put these two things in parallel, okay? Now when we put two things in parallel, what do we always need to worry about? The fact that we have a private communication, right? Cut always introduces a name restriction. So we have a private channel U, okay, along which Q communicates with P. Okay, P along U inputs an X, and then P of X is the one that actually provides the linear service that we have over here. Okay, so that's almost right, but not quite. Yeah?
You need infinite copies of the data.
Right. So this thing has to persist past the interaction, right? Because it might be copied many times. And the notation of the pi calculus for this is bang U of X. Okay. And in fact, Milner says in one of his papers that he chose this notation not by coincidence, but by some kind of analogy with linear logic. Okay. Even though it's a pi calculus expression, it's not even a constructor for a type or a proposition, it's just a constructor for a term. So let me rewrite this because it's hard to read. So we create a new name U. We P, which depends on X, okay, and we put that in parallel with Q. Okay. So this is what's called a replicated input or replicating input in the pi calculus. And can anybody guess what the rule is? I'll finish the lecture with that for actually doing this communication. So, so if I have a replicated input followed by P together with an output of a Y followed by Q, how do we reduce that? So we take P and we substitute Y for X, right? Okay, so that's the one communication. What else?
And then you keep the first process.
Yeah, you have to keep this, right? Because U is a persistent channel. So we keep bang U of X, P, and what else? Q continues because it's now output. Okay. Okay, and that's in fact the reduction rule for replicated input. Okay. And it's a special case of the general rule of replication, something like if you have a bang process, it's equivalent to bang P in parallel with another copy of P. Okay. So we only use it for the special case that this is a replicated input. Okay. We don't use the general replication. Okay. Okay. So this is how it works out. I can do all this so that even without, we're just talking about persistence, not talking about bang as a connective. So there's two more rules that have to annotate. Okay. But that's relatively easy to do, so I can dispense with that quickly at the beginning of the next lecture. But the important part is the copy rule interacts with the cut rule, okay, in this particular way. And bang of, so a persistent service offered along a shared channel means that you have to send it a name, and then you're going to communicate with a copy of that service along that name that you send it. Okay. And that service will continue to be there after the interaction. And in fact, will in some ways never go away. Okay. That's because like so once you have an assumption in gamma, in the whole proof above this, it's going to be available. It's never going away. Okay, last question on this before we call it a day. All right, so remember, yeah? You have a question? Okay. Okay, so remember, if you haven't handed in the homework yet, it's due sometime today. And I'll see you on Monday.